Hello everyone, my name is Kai and it's my pleasure to participate in ICISN 2021 to give you a presentation about my work with Dr. Phương Dao and my friend from Hanoi University of Science and Technology. The title of the report is Adaptive Reinforcement Learning Motion Force Control of Multiple Uncertain Manipulators. This is the outline of my presentation. First, introduction. Second, problem statement. Third, motion force control. Fourth, simulation results. And fifth, conclusion. Past decades have witnessed nonlinear control as a promising and powerful technique in designing control schemes for robotic systems. For cooperating mobile manipulators, CMMs, the control objective was classified into several situations depending on the control design requirement, trajectory tracking control or motion force control, centralized or decentralized control. However, almost existing control strategies for CMMs are implemented by a non-linear approach. As a result, it is difficult to handle the situation of actuator saturation and full state constraint. This paper considers a novel direction of employing the optimal control for CMMs with the adaptive reinforcement learning ARL technique. As we have known that it is possible to analytically solve Hamilton-Jacobi-Bellman HJB equation, it is an intermediate step of finding the optimal controller. To overcome these challenges, the approach using ARL technique is able to solve online the HJB equation to obtain the optimal scheme. So what is our problem? We investigate M tooling manipulators as shown in figure 1. The interaction between expert manipulators leads to constraint condition as depicted in the following equation. Xi Ig equals to 0. Eta is the joint vector of n tooling manipulators system. The dynamic equation of n tooling robot manipulators which constrain force by interaction between a couple of manipulators can be described as this equation. The control objectives is to obtain not only tracking of joints to desired trajectories, but also guarantee the constant distance between an effective pair of manipulators. Moreover, the motion force control objective is also mentioned in the Lagrangian coefficients. The consideration of ARL technique in control design has achieved optimality. This section we focus on motion force control scheme from multiple uncertain manipulators as described in figure 2. It will be seen that the robot control algorithm is a starting point of ARL-based control design. Furthermore, the stability will be mentioned in this controller. First, we analyze robot controller for multiple uncertain manipulators. In order to obtain the motion dynamic model, the constraint force J transpose lambda needs to be eliminated by multiplying the matrix P on both sides. and we have this to the completed motion dynamic model. The constraint focus can be obtained by FC. We see here toe parallel includes two members, toe parallel dependence and toe parallel dependence. Toe perpendicular for control force. The total control input is the sum of toe parallel and toe perpendicular. We have here the control law for toe parallel independence and toe parallel dependence. Based on the certainty equivalence principle, the robust adaptive controller can be defined as follows. In this section, we further extend the results in the previous section to ARL-based control design with the consideration of motion dynamic model and the appropriate tracking error model. It can be seen that tracking error model is time-varying system. As a result, it should be transformed into the autonomous system by using the additional term as defined TOD as the feed-forward term. We have augmented state variable x. Then we obtain the time invariant of phi system x dot. Therefore, the ARL-based controller can be proposed with performance index like this, V. We use neural network approximator to find the solution of HJB equation, V hat and U hat. Then the update law for critical weights and actual weights like this. In this section, the system contains two link manipulators. Is considered to simulate with the purpose of validating the proposed controller. The desired trajectories for 4 independent joints are like this. The initial condition for 3 manipulators are chosen as the responses of joint variables in 3 manipulator system and adaptation law for uncertain parameters are shown in figure 3 and figure 4 respectively. We can see in figure 3, all joint variables follow the desired trajectories. And figure 4 shows the convergences of estimated parameter. So in this paper, ARL-based motion force control have been proposed for solving the optimal control problem of multiple uncertain manipulators. The motion force control structure is given to develop the ARL technique based on motion dynamic model after the separation technique of cooperative manipulator was implemented. However, the control design requires the ARL-based solution for time-varying systems. For this reason, the additional terms TOD are proposed to handle these disadvantages. Finally, the online actor critic ARL is developed with neural network and optimality principle for modified motion dynamic model. So this is the end of my presentation. Thank you for your attention. If you have any question, feel free to ask. Thank you.